Guys, I'm Mohammed Kaif from Sri Venkateshwara College of Engineering. So I'm gonna explain about the Quicksort Einstein complexity derivatives. Introduction. The basic version of Quicksort algorithm was invented by Carr in 1960, formally introduced Quicksort in 1962. It is used on the principle of divide and conquer. Quicksort is an algorithm of choice in many situations because it is not difficult to implement. It is a good general purpose sort. It consumes relatively fewer resources during execution. Quicksort 1962. Select a pivot partition element. Rearrange the list so that all the elements in the position before the pivot are smaller than or equal to pivot. Those after pivot are larger than or equal to the pivot. Extend the pivot with the last element in the first sublist. The pivot is now in its final position. So that is A of I less than or equal to P, or it's A of I greater than or equal to P. Apply quicksort to the sort list 7 2 9 1 10 5 4. Description of quicksort. Quicksort works on partition a given array A of P to R into two non-empty subarray and A of Q plus 1 to R, such as every key in A of P is less than or equal to every key in A of Q plus 1 to R. Then the two subarrays are sorted by recursive calls to quicksort. The exact position of the partition depends on the given array. Index Q is computed as a part of partition procedure. Quicksort design follows the divide and conquer paradigm. Divide means partition separate the array of A of PR into two possible empty subarrays. Such each element in A of PQ minus 1 is less than or A of Q. A of Q is less than each element in A of Q plus 1 to R. Index Q is computed as part of partition procedure. Concur. Sort the two subarrays by recursive call to quicksort. Combine. So the subarrays are sorted in place. No work is needed to combine them. Quicksort. Like merge sort, quicksort is also based on the divide and conquer paradigm, but it uses this technique in somewhat opposite manner, and all the hard work is done before the recursive calls. It works as follows. Firstly, it partitions an array into two parts, then it sorts the parts independently. Finally, it combines the sorted subsequence by a simple concatenation. Quicksort algorithms consist of the following steps: divide the partition list, and then recursion, and then conquer. The partition links to partition the list. We first choose some elements from the list from which we hope about half the element will come before and half after. Then we partition the elements so that all those with values less than the pivot come in one sublist and all those greater values come in another. Recursively sort the sublist separately. Conquer put the sorted sublist together. Okay. And then next is quicksort procedure. If P is less than R, then Q partition of A of P R. Recursive call to quicksort. And recursive call to quicksort is A of Q plus R plus R. Partition choosing the pivot. Firstly, we have to select a pivot element among the elements of the given array, and we have to put the pivot into the first location of the array before partition. Which array item should be selected as pivot? Somehow we have to select a pivot, and we have that we'll get a good partition. If the item in the array arranged randomly, we choose a pivot randomly. We choose the first or last element as a pivot. We can use different techniques to select the pivot also. Example, the initially we have 2, 5, 8, 7, 3, 1, 7, and 6. And the pivot is like 6. So the iterations we have shown as here as the partition will going to be like this. And the next example is to be continued here. We have examples continued. The partition. Select the last element A of R in the subarray of PR as the pivot, the element around which to partition. As the procedure executes, the array is partitioned into 4 possibly empty regions. A of P to I, all the entries in the region are A of I plus 1, comma j, j minus 1. All the entries in these regions are pivots. And A of j to R minus 1, no, not known how they compare pivot the above hold before the each iteration for the loop and constitute for loop invariant. Complexity of partition. Partition time is given by the number of iterations for the loop, that is n is equal to r minus p plus 1. The next is the quicksort overview. To sort a left A of left to right, if left is lesser than right, partition A of left to right such that all A of left to P minus 1 are less than, or A of P and all A of P plus 1 to right are greater than or equal to A of P. Quicksort A of left to P minus 1 and quicksort P of plus 1 to right. And then next is the partition in quicksort. A key step in the quicksort algorithm is partition the array. We choose some any number p in the array to use as pivot. We partition the array into 3 parts, that are number less than p and number greater than p or equal to p. The next is alternative partition. Choose an array value to use as the pivot, starting from the left to left hand and the first element that is greater than or equal to pivot. Searching backward from the right end, find the first element that is less than the pivot. Interchange. That means that we have to swap these two elements. Repeat searching from where we left off until done. For example, as you can see here, choose the pivot, searching, swap, then again search, swap, and at last we have to swap with pivot. Best best case time complexity. The best thing that we could happen in quicksort would be the each partition stage divides the array exactly in half. In other words, the best to be the median of the key in A of P are every time procedure partition array to be sorted into equal sized array. If the procedure two regions of size n by 2, the recurrence relation is then T of n is equal to T of n by 2 plus T of n by 2 plus theta of n is equal to T of 2T n of n by 2 plus theta of n. From case 2 of master theorem, T of n is equal to theta n log n. Worst case complexity. The worst case occurs in if given array of A 1 to n is already sorted. The partition A P are called always return P successive calls to partition will split array of length n, n minus 1, n minus 2 to 2 etc. And running time proportional to n plus 1 and n minus 1 plus n minus 2 plus equal to n plus 2 and n minus 1 divided by 2 is equal to theta of n square. The worst case also occurs if a of n to 1 to n starts out in reverse order. So you can see the graph as mentioned. And then next is the worst case for quicksort. In worst case recursion, maybe n level stop, but the partition works at each level n still n. So the worst case for quicksort is 0 of n square. When does this happen? There are many arrangements that could make this happen. Here are two common cases: when the array is already sorted, when the array is inversely sorted. Typical case for quicksort. So we are gonna see the typical case. If the array is sorted to begin with, quicksort is terrible. If it is possible to construct other bad cases. However, quicksort is usually 0 and log to the log base 2n. The constants are good so that the quicksort is generally faster algorithm. Most rarely word sorting is done by quicksort. Okay. Then next, the conclusion. We have so long covered with this quicksort. Quicksort is an in-place sorting algorithm whose worst-case running time is n. An expected running time is theta of n log n, where constant hidden in theta n log n are small.